going to talk about Raman scattering, which is a type of vibrational spectroscopy that you can do that involves looking at how much light has changed when it is interacted with a molecule, in particular the molecular vibration. So, scattering. Actually, let's just say scattering. So scattering is when you have a redirection or so a photon traverses a material, but its energy or trajectory is changed. So photon traverses molecule with change in trajectory or change in energy. Now that's different than an absorption, to where you've got the energy of the angular momentum, or the energy of that photon is transferred into an energy state. Here the energy is carried with the photon. So the photon keeps going and it either picks up energy or loses some energy as it goes. A scattering that you're familiar with is Raleigh scattering. And that, so you are on the Earth, there's the sun, there's the atmosphere, you are rather tall, so light comes in. I'll use a black marker because I don't want to confuse us. So light comes in, and some of that light is going to come through, but some of it is going to scatter. So it's just changed its trajectory, not changing its energy. Now, what's called the probability, it's the collisional cross-section, is proportional to 1 over lambda to the 4th for Raleigh scattering. Don't need to know what that means, except for this is the likelihood of scatter. And for those of you that took thermo with me already, or with Deanna, this is that same cross-section from collision theory. And it relates to inverse lambda to the 4th, where lambda is your wavelength. So when light comes in, you have 400 nanometers to about 600, about 700 actually, in the visible. Well, which of these is going to be scattered the most? Smaller number here, bigger number here. So the 400 is going to be scattered much more, which is why this is all blue light. And that's why the sky is blue. Yay! You should see the mathematics behind this. It's quite lovely. Anyway, so if we turn the Earth, we rotate such that now you are right here, because the sun doesn't move, we do. So actually, let's move us right about here. Okay. So as the light continues to come through, when it goes through this part of the atmosphere, the blue is immediately scattered. Blue. But then as you go through a longer path length, you're going to arbitrarily, say about right there, you're going to start to get the longer wavelengths will start to scatter. And this is where red will start to scatter and yellow will start to scatter. And so that's why sunsets are red, or sunrises, is because of the length of the atmosphere that the photons have opportunities to increase the likelihood of scatter. So it goes like 1 over lambda to the 4th. That doesn't mean that red light doesn't scatter. It's just the intensity of the blue light that scatters is much, much more. Go team. Raleigh scattering. So for every Raleigh scattering, this happens so often, light scatters like crazy. And so if you have a laser and it's shining at a material, there will be 99.999% of the time there will be a Raleigh scatter. But every once in a while, and this means that there's going to be some energy associated with this laser wavelength going in, and there's going to be that same wavelength as it goes out. So the same energy, it's just changed its direction a little bit, much like, exactly like what happens with the sky's blue. Okay, but 0.0001% of the time, when the light comes in from the laser and it's deflected in a different direction, it's going to have a slightly different frequency. slightly different. And that slightly different is corresponding to a difference in a vibrational energy mode. Yay! Raman scattering. And so you can have so the laser light comes in and hits the material, and when it comes out, if it's H nu plus the energy of a vibrational mode, so the light comes in, and if it leaves plus the frequency of the vibration, so this is now gone an increase, minus. So it's now lost a little bit of energy. So the vibrational mode, so the light comes in, and when it changes its direction, it loses a little bit of energy, and that goes into an increase in the vibrational mode, such that the light that comes out now is lost that frequency. That's called a Stokes shift, or Stokes scatter. Cool. Now, if the wavelength or the vibration is already vibrating at a higher energy state, and the light comes in and it gains that energy, so the molecule's in a higher vibrational mode, and then what happens is the photon comes in and it takes that energy and it reduces the energy of the vibration, so the vibration now goes down to a lower energy state, and so that means that the photon has gained some energy. That's called so nu plus nu vibrational, that is called an anti-Stokes scatter. Named after George Stokes, who discovered fluorescence as a technique. Go team. That was like in 1852. Hooray. Okay, so that's Raman scattering. And the cool thing about that is the way that it works, the same way that you have a transition dipole moment for IR. So psi final, dipole moment, psi initial, d tau, non-zero, you have a transition. If this is what's called the dipole moment derivative, which means you have a molecule, let's say, and it has a dipole, and that dipole is oscillating upon the vibration. So mu permanent oscillating, you have an IR active mode. Okay. If, however, instead of this being a dipole moment derivative, it is a oscillating polarizability, then you have a Raman active mode, such that an oscillating polarizability is going to be, let's take hydrogen, H2, non-polar, right? But if we put this across an electric field, let's make it this way. So electric fields are always drawn in the direction that the positives would go. So that means that if I draw this hydrogen, its electrons would scooch that way. Go team. So we have caused an induced dipole through polarizability. Sure. Okay. And so you can think of that as if the electric field were coming this way, the electron density would shift down. Born-Oppenheimer lets us separate those two. So don't forget, these two are essentially kind of staying in the same place while we move the electrons around. Okay, so this is a polarizability. And that's what that represents. So this is called the polarizability tensor. And if this, when it operates on the wave function, gives you non-zero, yeah, you have transition. We don't need to go there. We won't. This is, if you're pursuing physical chemistry spectroscopy in graduate school, you might jump into this. But this is for really into the weeds of how Raman works. But what's beautiful is that it's the same transition dipole moment. It's just the operators are different. In one case, you have a transition dipole moment being caused by an oscillating dipole, IR active. Another time you have it being caused by an oscillation of the polarizability or the polarization, which is Raman active. Okay, I'm gonna pause for a second and erase all of this. Okay, so just to add all that up together. So IR active, so vibration causes oscillating dipole. And for Raman active, vibration causes oscillating polarizability. And again, psi mu psi d tau not equal to 0, psi alpha e psi d tau not equal to 0. Go team. Okay, here's an example. We're going to do carbon dioxide, and then I'm going to show you some benzene stuff. It's pretty cool. Okay, carbon dioxide. First, ask yourself, how many modes of vibration? So we've got 3n minus 5. 5 because this is linear. That gives us 3 times 9, or 3 times 3, 9, minus 5, 4. So we've got 4 normal modes. And they are, so you can have this, this asymmetric stretch, which is if my head is the carbon and my arms are the oxygen, it's like this. Cool. And so this causes a change in dipole moment because normally, so polar, total gives you non-polar, but if this shrinks and this grows, then you're going to have a change in the dipole moment, which is an oscillating dipole. That becomes non-zero. This is IR active, Raman inactive. Because as you change, this decreases and this increases, it's an equal and opposite change in polarizability. Unlike the symmetric stretch, which causes, if you think about it this way, so carbon's really stretched out. So as it really stretches out, you're going to have, so as it stretches out, if the electron density, now this region is much more malleable, so it can really bend down, likewise bend down in the presence of an electric field. Which, think about what a photon is. It's really just a moving E field and B field, constant changing. And depending on the strength of that E field or B field, i.e. the frequency of it, big E field, little E field, big B field, little B field. And so that's the induced electric field that's causing the oscillation, okay? Which is why it's different than an absorption. Oh, sorry. So this one is Raman active, and this is IR inactive. So what's really fun about IR and Raman, if you're a good vibrational spectroscopist, you have both. And if you're really good, you have both and then multiple versions of both. And with the IR, you would actually go into the near, and then so you'd have near IR, mid IR, and far IR, which go the full range of the IR. And with Raman, other thing, I already told you, with Raman, it doesn't matter that you have the wavelength in doesn't have to equal the transition. It's a scattering technique. So you can use any incident light. Any incident light will Raman scatter. There is Raman scattering happening right now from the LED light that's coming off, just blinded me, that the LED light that's coming off, and if I move around, the fluorescent light that's going to hit me on the other side would also Raman scatter, 0.000001%, but it doesn't matter the incident light. So if you have monochromatic, i.e. a laser with a high throughput of photons, huge power, you can then have a detectable scattering signal. Hence why I have on my Raman downstairs. I wish I had a Raman downstairs. Well, I have a lamp. Technically, everything Raman scatters, just very small. So at the lab, we've got 2 different wavelengths of light: 532 nanometer laser and a 785. The 785 is fantastic because a lot of times in the visible, you're going to induce fluorescence. If you induce fluorescence with the Raman, that's a bad thing because this is such a faint signal when the light comes off. It's such a very, very faint change in frequency that if there was an electronic transition at the same time and that induced a photon, that would be like, this is a water gun that I'm holding, and then this is Bobby behind me with a fire hose. You can't tell the difference between the photons. And so that's one of the reasons that fluorescence is such a bad thing. I digress. I love Raman. It's really fun. Let me show you some spectra. Okay. Where's my mouse? So the first spectra I'm going to show you is benzene. Benzene. Okay, so 1, 2, 3. I don't even know how many molecules. Figure out the number of vibrational modes there are, right? Lots of IR and Raman active ones. Okay. Share screen, share screen. Okay, so here we've got transmission IR and we've got Raman. So the black is the transmission IR, the red is the Raman. So you can see any good spectroscopist would look at both the Raman and the IR and do a comparison. So you have information in certain modes in the Raman that you don't see, like this peak right here. Yeah, don't see it in the well, you don't really kind of see it. This one definitely don't see it in the IR. But because of inharmonicity, you are going to have some IR active and Raman active simultaneously, because as you couple some of these vibrational modes together or rotations, you're going to have some overtones and other transitions that are kind of semi-allowed. Okay, let's see, who can we talk to? So this, look at the black one. I believe this one, actually no, it'd be much, much stronger, is the breathing. Oh, the breathing, that's really cool. So that's where this whole thing is like expanding. And then you've got the CH stretch of the aromatic, so 3000-ish. But let me show you some of the many vibrational modes of benzene. Isn't that cool? This is at Purdue. I love this website. Look at all of them. So you've got IR inactive, Raman active. So that's that large peak at 3000. And so there's a breathing mode. And so IR inactive, you have no change in dipole moment here, but you do have a change in polarizability as that ring shrinks and grows and shrinks and grows. You have a slight IR intensity, Raman inactive, IR active, IR active, Raman inactive. I mean, there are so many. There are so many. 3n-6. Some of these are really cool. This is where I'm going to get my dance moves. So Raman active, IR inactive. Cool. So just because you have an IR active molecule doesn't mean that it's not Raman active in some form or fashion. You've got to look at each individual vibrational mode, which wouldn't necessarily be just the molecule or the vibration bond right there. You've got entire molecules wiggling and jiggling about. And as you go into lower and lower frequency, you're going to get to the more whole molecule vibrations. Let's go way down. Isn't this crazy? There we go. There's one. So this is at 618. This is the quote fingerprint region. So you've got very, very subtle motions. 648, you've got Raman active. This is kind of the shoulder shake. And so again, very, very subtle vibrations because they are a low frequency, but interesting nonetheless. Okay, who else do I have? Here's CO2 in the IR and the Raman. So 2 vibrational modes in the IR, are active, and then only one in the Raman. This is the bending mode, and there's actually 2 of those. If you recall, we determined that there were 4 vibrational modes of CO2. This one is where there's symmetry associated with this oxygen going in the opposite direction. You can also have it where one of these 2 go in the same direction, and this one comes. It's kind of a weird offset, and that's much lower frequency. Cool. Okay, last thing I want to show you is every time that y'all, if you recall going to in Orgo, you would take IR of whatever, but you would always get a background first, and it would look something like this. Does that look familiar? Go team. What you're seeing is the IR of oxygen, or sorry, of not oxygen, oxygen's IR inactive, which is why it's not a greenhouse gas. Go team. Same with nitrogen, but CO2 is. So CO2 is IR active, which means it is a greenhouse gas. I should have led with that. Anyway, so when you're doing your IR and you get your background, there's your bending mode of water, your asymmetric stretch of water, and you get those 2, well, the main one. The bending, I actually very rarely see this one when I'm doing it, but this is very deep CO2 asymmetric stretch, which just tells you that there's CO2 in the atmosphere. Sigh. That's meta. Anyway, right. I hope that's cool. And the H2O bending, this is water vapor. Look at those rotational bands you can see. Oh, Q branch. That's awesome. Same with the symmetric stretching. So cool. So many different really neat applications. Once you start to learn the language of spectroscopy, you start to see and learn more and more. So I hope you've enjoyed this rendition of Allison talking. That's all I got. Iron Raman, so cool. If you have any other questions, please let me know. Yeah, I've done quite a bit of Iron Raman. Love to chat. Go team. Peace out. I won't do that again, I promise.